Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about separable equations. So basically, a separable equation is a first order differential, meaning the highest derivative that we see is 1, in which the expression for the slope, or dy over dx, can be factored as a function of x times a function of y. And it basically can be rewritten in this format. Again, we see this function of x times the function of y. In this case, we can say it's a separable equation, and we can kind of see how we're going to be solving these later on. Now, separable equations help us solve initial value problems as well as just differential equations fairly easily if they can be written in this format right here. So the way we can go about it is we can say that, let's say h of y is equal to, 1 over f of y, provided that, f of y is not equal to 0, so we don't get a division by 0 error. If we say this, then we can get that dy over dx is equal to g of x over h of y. And now if we cross multiply upwards, we're going to get that h of y dy is equal to g of x dx. And now we can kind of see the integral already starting to form. We have a function of y, and we are going to be taking, if we had an integral sign, we would be taking that with respect to y. And on this side too, we could see that we would have a function of x, and we would be taking the integral, if we had one here, with respect to x. So everything's kind of lining up, and that actually is going to be our next step. What we're going to do is we're going to take the integral of both sides. And this right here is essentially what we use to solve separable equations. We want to take the integral with of the y function with respect to y, and then we want to set that equal to the integral of the function with respect to x. And again, this definition might look kind of wonky right now, but I'm going to show you two examples of how we can apply this to solve not only regular differential equations, but initial value problems too. So let's say we were given this problem right here, where y prime is equal to x squared over y squared, and we were asked to solve it. This right here is a prime candidate for the separable equation because, well, we see two functions, one with respect to x and one with respect to y, and we see them both being multiplied by each other. Now, don't be fooled, they're not being divided. It's basically going to be 1 over y squared times x squared. So it's essentially two functions. They're just written kind of squashed together. Now, again, we want to kind of rearrange this to write it in this format right here. So how can we do that? Our first step is going to be to switch this dy, or this y prime, to dy over dx using Leibniz notation, and then we're going to keep everything as it was. Now we want to cross multiply, so we get y squared dy is equal to x squared dx. And now this is the perfect time to take the integral of both sides. Perfect. Now we have two integrals, and we can easily compute the integral of both of these. There we go. We have computed the integral of both sides, and now all that's left to do is rearrange and solve for what y equals. So we have y over 3 cubed is equal to x cubed over 3 plus c. We can multiply both sides by 3. We're going to multiply this entire side by 3 to cross out these 3's and essentially start isolating for y. So we get that y cubed is equal to x cubed plus 3c. Now we want to isolate for y, so we take the cube root of both sides, and we're going to be left with y is equal to the cube root of x cubed plus 3c. And now we sort of want to get rid of this 3c and write it a little more generally, so I'm going to say that y is equal to the cube root of x cubed plus k, where k is equal to 3c. So there we go. We have solved our differential equation. Now, the second part to a question like this, maybe part B, would be, well, what if we had the initial value problem and we had this additional constraint that y of 0 is equal to 2? How would we go about that? Well, we already have the function here, right? And essentially, if you remember from initial value problems, the initial value problems doesn't look for a family of curves like this equation right here is. This is a family because of that constant k, but we want the exact curve. So we should understand that we would be solving for this value k, so that the only variables that we would be left with are x and y, which would be coordinates. We would have no other variables in our function. So let's go ahead and start with that. So we'd have y equals to the cube root of x cubed plus k. And now, because we are given that when x is equal to 0, y is equal to 2, we can simply plug that in. So y equals 2, then we take the cube root of 0 cubed plus k. So we end up getting that 2 is equal to the cube root of k, and k is equal to 8. So that would be the solution to our initial value problem, that y is equal to the cube root of x cubed plus 8. That is the solution to our initial value problem. And now you can see that this right here is a defined curve, whereas the answer to the just the differential equation was a family of curves. So here's another quick example. We have y prime is equal to x squared times y, and we need to solve for the solution family of curves, essentially. So again, the first step is to change this y prime to dy over dx, so we can start formatting our integral. Now we want to sort of break apart this right hand side function and split it up so that the y's are all on the left and the x's are all on the right. Again, right here it's important to realize that this can be rewritten as just 1 over y times x squared. So what we're going to do is we're going to have dy over y on this side, and then we're going to have x squared dx on this side. And from here on, it's good to bring the integral in. And there we go. We have the integral of both sides. Now, the left-hand side will evaluate to ln absolute value of y, and the right-hand side is going to evaluate to x cubed over 3 plus c. Now what we want to do is we want to evaluate for y. We want to solve for y because we want a function in terms of y. So how can we do that? Well, we know that if we raise both sides to the power of e, we know that those two functions are inverses of each other, so the only thing that we're going to be left with is the parameter into ln, which will be the absolute value of y. But if we raise the left side into the power of e, then we're going to need to do the same thing on the right side. Now we can simplify this and say that the absolute value of y is going to equal to the e x cubed over 3 plus c. Now to get rid of this absolute value, we can just say that y is equal to plus minus of e cubed over 3 plus c. And now using our exponential laws, we can break down this even further to say that this is equal to plus minus e to the c e times x cubed over 3. Now again, we want to generalize, and we don't want this c in here because it's not kind of just a single variable. So what I'm going to do is I'm going to say that a is equal to plus minus e to the c. And essentially a will be able to cover all of the numbers, so it can be positives or negatives. So I'm going to say that y is equal to a e x to the power of 3 over 3, and that is the final solution for this differential equation right here. So that's it. Just a quick little lesson on separable equations. Basically, this teaches us how to solve initial value problems like algebraically almost. It also teaches us how to solve regular differential equations, which can be written in a certain format. So that's it for today's video. I hope you enjoyed it and learned something. If the video has helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.